In this section of Chapter 10, we're going to be talking about forming alkynes via elimination reactions. So what we're going to see is that the vinylic position is resistant to nucleophilic attack and to elimination as well. And we talked about this in our previous chapter with those sp2 hybridized carbon atoms. When we talk about the vinylic position or the vinyl position, we're specifically talking about those sp2 hybridized carbon atoms. So in order to run a nucleophilic attack, or in our case to run an elimination reaction, we have to use really, really extreme conditions. So it's not just enough to use a base like OH-. We would have to use a base with a lot of heat as well to really get us, and this would be our thermodynamic control. We would be running the reaction based on getting to a more stable product. Or we could run this reaction under very extreme basic conditions, so using things like NH2-. The very extreme base conditions, this would be more of our kinetic control. The product would be predicted because of how fast the product we would form. The problem with both of these conditions is that both conditions will lead to very different products, but also under these very extreme conditions, if there's any other functionality within the group, we could see other secondary reactions or side reactions happening as well, which is why they're what we call extreme conditions. So specifically looking at this reaction that we're talking about, alkynes via an elimination reaction. So remember, for elimination, we do have to have a halogen, but now we're going to put that halogen in a vinylic position. So one of the ways that we can create the alkyne is through the use of a base and heat, or a base and heat. So NaOH and our heat as well. Remember, under these base and heat conditions, it leads us to our most stable product. So in this reaction that we would be looking at, we're actually going to end up generating an internal alkyne. So the internal alkyne is going to be more stable for us in terms of the amount of bonds that we have between carbon and carbon. The sp carbon to the sp3 carbon, we now have 2 of them in this internal alkyne, which is leading us to a very stable product, a more stable product based on bond strengths. The other option that we had under our conditions is to use the very, very, very strong base. So I'm just going to use NaNH2. We would have to follow this one up by an acid wash in order to get to our final product. But in this one, we would end up producing the terminal alkyne from the terminal alkene that we had. This is now the faster product that we would be producing. It's really the kinetic control instead of the stability control. So let's look at the mechanisms associated with each one of these. So starting off with the one with our base and our heat, we are going to see a deprotonation. This deprotonation of the carbon atom adjacent to the carbon with the leaving group would then drive off that leaving group as well. And initially this would generate for us that terminal alkyne. But since we are under these heat conditions, it does not stop here since we're under our equilibrium conditions with the heat. That because now we have these protons adjacent to the terminal alkyne and under these basic conditions, we're going to see another deprotonation happen. which ends up generating a carbanion to that carbon adjacent to the terminal alkyne. This can then undergo resonance since the electrons and the lone pair are adjacent to pi bonds. We will see a resonance structure. Where we're just going to move the pi bonds and we're going to move the lone pair of electrons. So we still see this nice linear structure, but now that carbon atom has two double bonds on either side of it. From here, we did generate water as well through that deprotonation. So we will reprotonate the carbanion that we generated. So we end up with this structure that has two double bonds side by side. From here, we're still under our basic conditions, so we are going to deprotonate once again. So again, now we have our carbanion from our deprotonation, but since that carbanion is next to pi bonds, we will see resonance structures. So now we will reform that triple bond, leading us to the carbanion as well. That carbanion will then pick up a proton from the water that we generated. Which will lead us to that internal It will lead us to our internal structure. And I have gained a carbon atom, so we'll be deleting that. I've gained the carbon atom. So it should only stay 4 carbon atoms throughout the whole entire process that you would be looking at. But basically, because we're under these extreme conditions with the hydroxide, we will see that we need to get to the more stable product. So we will see those conditions drive our proton transfers to get from the terminal alkyne to the internal alkyne, which will be more stable under these basic thermo conditions. So now let's look at the other mechanism where we were under the extreme base conditions. So with this one, we had the NH2 unit that was negatively charged, so we had that very, very, very strong base. We're going to see it come in and do the same initial deprotonation that we saw with the other condition. That initially produces for us that terminal alkyne. But under these conditions, since it's such a strong base condition, what is going to change for us is that very strong base is going to deprotonate the terminal alkyne. So this is why we need, in this condition, we had that second step, which was going to be the acid wash. So this is all happening under that kinetic control instead of looking for stability. So under kinetic control, we get to this terminal alkyne that gets deprotonated under our basic conditions. So then when we use our acid wash, the acid wash will reprotonate that terminal alkyne, leading us to our final product. So those would be the biggest change in conditions that we would be looking at between producing the kinetic product, the terminal alkyne, or producing the thermal product, which would be the internal alkyne.